So, now we start the construction of the Lebesgue measure using Riesz representation theorem, which means we have to define a positive linear functional on Rn, and Riesz representation theorem will give us a sigma algebra and a measure. So, the sigma algebra is going to be the Lebesgue sigma algebra which we have seen earlier, and the measure is going to be the Lebesgue measure, and along with it all those properties which some of which we already know, like outer regularity and inner regularity for sets with finite measure, and the sigma algebra is complete. Since Rn is sigma compact and every open set is sigma compact, we know the measure is going to be regular. So, in particular the Lebesgue measure will be a regular Borel measure on Rn. Okay, so let us start the construction. Construction of the Lebesgue measure. Lebesgue measure using Riesz representation theorem. Okay, so this is the second construction you are seeing. There is another approach due to Carathéodory which we will not be doing, but I will give you some references for that. That actually works in a much more abstract setting. So, let us look at R to the k. So, we change the notation slightly, instead of Rn we will use Rk. So, some simple definitions first, which you have seen already. We have used the term cubes, rectangles, etc. Now, we slightly change it because I am following Rudin's book, Real and Complex Analysis. Okay. So, a set of the form say W equal to product of intervals alpha I, beta I open, okay, I equal to 1 to k is a K cell, Of course, sometimes one may change this to alpha I, beta I, or alpha I open, beta I closed, etc. So, this is simply a rectangle in our earlier notation. So, this is a rectangle in the earlier notation, okay, or terminology. And of course, it has the volume which we already know. So, volume of W is simply the product of the length of the sides. So, beta I minus alpha I equal to 1 to k. Now, if I take a point, if A equal to, let us say, alpha 1, alpha 2, etc., alpha k. So, this is a point in Rk, and delta is positive, then the delta box or the delta cube with corner A. Corner A is denoted by, so, Q A delta. So, this is simply the product of I equal to 1 to k, because we are in Rk. So, there are k intervals alpha I to alpha I plus delta. Okay. So, you simply look at delta. So, this is a cube with sides length delta, and the left hand bottom corner is A, right. That is what is meant by this. So, let us look at R1. In R1 there is only one coordinate. So, I will have some alpha and alpha plus delta, right. So, it is this. In R2, so if I take a point here alpha 1, alpha 2, well, what do? You go this way to alpha 1 plus delta to alpha 2, and similarly here and similarly here. So, you are only choosing the, so this, the right hand side is open, okay. So, you are only choosing this portion, this is contained, and you have all the interior points, but not the boundary on the top right hand corner. So, the corner portion is here, that is the that is A for you, and you look at a delta cube cornered at A, right, that is what we are doing. So, now some notation for n equal to 0, 1, 2, 3 and so on. Let Pn be the set of all points, all x in Rk. So, remember k is the dimension whose coordinates are. So, I am fixing an n for Pn. Pn is the set of all points whose coordinates are 2 to the minus n times integers. Okay. So, let us try to understand this a bit more clearly. So, when n equal to 0, 2 to the minus n is 1. Okay. So, P0 is all those points x in Rk such that x1, x2, etc. xk, they are all integers, right. N equal to 1, well, 2 to the minus 1 is half. So, P1 is all those points such that x1, x2, etc. xk will be in 1 by 2 times z, right. So, 1 by 2 times z. So, in particular this will contain P0. Okay. So, let us look at P0 and P1 in the dimension 1 case, because that is the easy case. So, 0, 1, 2, minus 1, minus 2 and so on. So, P0 is just integers, right. P1 is you divide all of them by half. Etc. So, you have divided everything in P0 by 2, that is what you are doing, and you continue. Okay. Let omega n, so we have Pn, Pn's are simply coordinates, omega n is going to be collection of box, be the collection of all 2 to the minus n boxes. So, what is 2 to the minus n boxes? Remember the delta boxes. So, if I take delta, I know what is a delta box. So, 2 to the minus n box meaning the side length is 2 to the minus n, right. So, 2 to the n minus meaning side length is 2 to the minus n. Well, so what are the corners for these boxes? Corners are in Pn with corners in Pn, right. Pn is all those coordinates with this property. Okay, so let us see what is omega 0. So, omega 0, what is omega 0? Collection of all 1 boxes with corners in P0. P0 is just integers, right. So, we have 0, 1, 2, minus 1, minus 2, etc. This is P0. So, box with corner at 0 of side length 1, what is that? That is this interval. A box at corner 1 and length side length 1, so that is this, etc. etc. So, this partitions real line into intervals. Well, what will be omega 1? Well, first of all, corners are at P1, which means you divide all of them by 2. So, you will get minus 2, minus 3 by 2, minus 1, minus half, 0, half, 1, 3 by 2 and 2 and etc. etc. And what is omega 1? You look at 2 to the minus 1 boxes, that is half boxes. So, side length is half with corners in P1. So, corners are here and length half. So, all that you are doing is the first one, which was this, you divide that into 2, right, and you have this one, this and so on. So, all the previous ones are divided by 2. This is what is happening in the real line. Similarly, if you look at R2, you will see omega 0. Well, omega 0 is, first of all you have to find corners. So, you have 0 0, 1 0, 2 0 and 1 1 0 1 etc., etc. So, it will be boxes of this kind, that will be omega 0. Omega 1, well, you have to find the corners first. First you divide these things by 2 and so on, right, and then you will be dividing this by 4. That is because there you are in dimension 2. In dimension k you will divide this into 2 to the k boxes, right, and you continue. Next time you will have further divisions like this and so on and so forth. So, that is the collection of boxes we are looking at. Okay. So, there are properties of this. So, let us write down some properties. If n is fixed, so remember n is not the dimension, k is the dimension, n gives you the corners and the boxes and so on, n is fixed, each x in Rk lies exactly in one member of omega n, exactly in one box in omega n, right. So, that is clear from the picture, right, each time. So, first time you have partition. So, if you fix n equal to 0, any point will be in one of the intervals. Similarly, if you fix 1, that is your n, then any point will be in just one interval, because these are all partition. Each time you are dividing the earlier intervals by half. In R2 you are dividing each square into 4 squares, right. In R3 you will be dividing into 8 cubes and so on. So, in Rk you will divide each box into 2 to the k boxes to go to the next level. So, in each time it is a partition of this whole space, and so any point will lie exactly in one box. Okay. So, that is one. Second, if q belongs to omega n and q tilde belongs to omega r, where r is less than n, then either q is contained in q tilde or they are disjoint. Q intersection q tilde is empty. So, this is a pretty trivial observation, even though it might sound very complicated. Let us take omega 0 and omega 1. Okay. So, n is 0 and let us take r equal to 1. So, r is, sorry, the other way, right. So, r is 0 and n equal to 1. So, r is less than n, right. What this says is, if I take any box from here, so let us say this interval, this will be of course contained in one of the intervals here, right, or it is disjoint from any of these intervals. That is because the intervals here are obtained by dividing the intervals in the bigger set, right, in the previous level. So, at each level you are dividing the intervals into 2 equal halves to go to the next level. So, when you compare it with previous boxes in the previous level, either they are contained inside one box or they are disjoint. So, that is very easy to see. Okay. The next one requires a little bit more thought. I will leave it to you. If q belongs to omega r, so that is at the rth level, volume of q, this is trivial, is 2 to the minus r k, because you are in dimension k. So, each volume, so you have k intervals and each side has length 2 to the minus r. So, it is 2 to the minus r k, that is trivial. And if n is greater than r, Pn has exactly 2 to the n minus r k points in q. So, if n is greater than r, you will be dividing q again and again, right, to go to n. So, you will start from r, you go to r plus 1th level, r plus 2th level, etc., etc., and you land at n. At each time you are dividing each cube by 2 to the k cubes, right. So, at each time you will get 2 to the k cubes. So, there are n minus r levels and that will give me 2 to the n minus r k points. Okay. So, do it for k equal to 1, it will be very clear to you. Okay. So, let us see, we need one more property D. This is something which you have seen already. Every non-empty open set in Rk is a countable, so that is important, disjoint union of boxes in omega n. Of course, you have to take the union for 0 to infinity. You look at all the omega n. So, these are boxes and you can write any open set as a countable union of boxes from this. So, that is pretty easy because we have done this before for writing an open set as a countable. So, let us recall that part. So, recall the proof of open set being an almost disjoint union of cubes. So, we did that, closed cubes. Okay. So, we had cubes like this and there was intersection at this middle. But the boxes are such that we are only looking at this part, right. The top part is not there in the box, right. So, when I take an adjacent cube, they are sort of disjoint. Okay. So, that is what you should understand. So, that is why we get a disjoint union. Okay. If you take the closed cubes, then you will get almost disjoint. But the cubes we are looking at omega n, these are 2 to the minus n boxes with corners in Pn. When I say a delta box, remember this right hand side is open. So, because of that these boxes are disjoint. Okay. So, that is the reason you get disjoint ones. Okay. So, we will stop with the statement of the theorem, and which actually gives us the Lebesgue measure. So, keep in mind all the omega n's and so on. So, there exists a positive complete measure M, this is the Lebesgue measure, and a sigma algebra script M, which is actually the Lebesgue sigma algebra in R to the k, such that several properties. So, all of this most of it you already know. Measure of a a k cell W is the volume of W for k cell W. B, the Borel sigma algebra of Rk is contained in M. Okay. Also, a set in M if and only if there exists. Okay, so let us use E because that is the standard thing we have been following. E in M if and only if there exists A, which is an F sigma, and B, which is a G delta, such that A is contained in E, contained in B, and measure of B minus A is 0. And the measure M is regular. So, we have seen this regularity. Now, it is completely regular, it is not outer regular for all sets and inner regular for sets with finite measure. It is regular for all Borel sets. Okay. M is translation invariant. We know this, but more importantly, if mu is any positive Borel measure on Rk such that mu of k is finite for every compact set k and mu is translation invariant, then mu equal to some alpha times m, it is a multiple of m. So, this is like the uniqueness of Lebesgue measure. Any reasonable translation invariant measure is a multiple of the Lebesgue measure, there is nothing else. Okay. So, the last property, if I have a linear transformation, okay, linear, there exists a number which we call delta t. This is actually going to be the determinant of t, we will compute this later, such that the measure of Te, so that is the image of E, right. So, you have to prove that Te is actually measurable, is actually equal to delta t times me for every E in m. Okay. So, recall that we did something like this by multiplication by delta dilation. When we looked at dilation of Lebesgue measure, we saw that delta to the n comes out, which is precisely the determinant of the linear map x going to delta x. So, that is the delta t here. Okay. Okay, so we will stop here. So, we have just written down the theorem which constructs the Lebesgue measure out of Riesz representation theorem. In the next lecture we will look at the proof. So, this would be by constructing a linear functional which is positive on Cc of R, compactly supported continuous functions on Rk in fact, and that will give us the Lebesgue measure along with the properties which we have already seen. Okay.